Okay, we're still talking about simple harmonic motion, the second problem here that we're covering in homework 41. It is problem 53 on page 5, 54. It's got a sister problem 51, simple harmonic motion associated with tuning fork. So maybe I've brought a tuning fork into class. It's an instrument that's used actually, it's given its name tuning fork because it produces an audible frequency that can be used to tune musical instruments or whatever with, and it does so by, once striking it, there can be many modes of oscillation, but the mode in which these things move back and forth is the mode that lasts longest, and it is at a specific frequency that, like I said, makes a sound, makes an audible sound. Good Lord. So here's what the problem says. It says, I'm trying to draw something which is oscillating. So this problem says the end of a tuning fork moves in simple harmonic motion given by D is equal to A sine omega t. My pen has given up on me. So the D actually is this kind of distance right here. My pen has given up on me. And if a tuning fork for the note A above middle C on the even tempered scale, A4, the tone by which an orchestra tunes itself, has a frequency of, 440 hertz, which, by the way, a hertz is a cycle per second. A hertz is equal to one cycle, or it's equal to number of cycles per second. It's a cycle per second. Okay. What's the question here? Find omega. Okay, that's the problem that we're working on. Pretty simple. Omega is radians per second. The frequency f is cycles per second. So if we divide omega by 2 pi, the radians, it's radians divided by radians per. Omega is radians per second. Let's divide it by 2 pi, which is the number of radians in one cycle, and we end up with cycles per second, which is f. All right, so if we want to find omega is equal to 2 pi f. In this case, it's 2 pi times 440 cycles per second, and so omega is going to turn out to be 440 enter 2 times pi times, it's going to be equal to 2.7646 times 10 to the something third radians per second. Yep. A lot of radians whipping around there. And the second problem says if the maximum displacement at the end of the tuning fork is 0.01 millimeter, I'll come back over here. If D is equal to 0.01 millimeter, then what equation do we have? It's right here. The equation that we're talking about then is D of t is equal to 0.01 sine omega t, and there's the omega that goes into this. Okay, we'll leave it like that.